today we're going to be solving some practice questions from OCR Physics on Circular Motion. The questions are always applicable to all exam boards. So if you're doing AQA or Edexcel or any other exam board, then this will be very valuable practice. The best way to have a go at this video will be to solve the questions first, and you'll be able to find links to the individual questions in the description of the video, and then check your answers with the video. Just a little note, these are not official solutions, these are just my solutions, and to have a look at the official mark schemes, please visit the OCR website, and I provided a link to that in the description of this video. Okay, well, let's have a look at this question, which is question 2 from January 2010. So figure 2.1 shows the London Eye, and we have a little drawing here of the London Eye. It has 32 capsules equally spaced around the edge of a large vertical wheel of radius 60 meters. The wheel rotates about a horizontal axis such that each capsule has a constant speed of 0.2 meters per second. Calculate the time taken for the wheel to make one complete rotation. Okay, well, the first bit of that question, we can just simply use the fact that the speed is constant in circular motion, so V is 2 pi r, which is the circumference divided by the time period. Rearranging this for t, we're going to find that t is equal to 2 pi r divided by the speed, which is equal to 2 pi multiplied by the radius, which is 60 meters, so a very, very large wheel, divided by 0.26, and this will give us 1450 seconds. Okay, part 2. Each capsule has a mass of 9.7 times 10 to the power of 3 kg. Calculate the centripetal force which must act on the capsule in order to make it rotate. Well, this is just the centripetal force equation, so we're going to be using F is equal to mv squared over r. The mass is 9.7 times 10 to the power of 3. Now, I'm not going to forget to square the speed, that's why we'll put in some brackets. The speed is 0.26 meters per second squared, and then I'm going to be dividing that by the radius, which is 60. And if we put that into a calculator, we're going to get about 10.9 newtons. Okay, part B, figure 2.2 shows the drum of a spin dryer as it rotates. Then we have a dry sock is shown on the inside surface on the side of the rotating drum. Draw arrows on the figure to show the direction of the centripetal force acting on S when it is at points A, B, and C. Okay, first off, just a little note that you should be drawing this with a ruler in the real exam. I don't have a ruler for my digital whiteboard, so let's draw this. Now, in each of those points, the centripetal force will be acting towards the center. So at point A, we're going to have a centripetal force acting towards the center. At point B, we're going to have a centripetal force acting towards the center. At point C, we're going to have a centripetal force acting towards the center. Okay, part 2, state and explain at which position A, B, or C the normal contact between the sock and the drum will be the greatest and the least. Okay, well, the normal contact force, I'm going to call that N, will be the greatest at C. So this will be one of the marks. So the first part of my answer is just simply to say that at C. Now, why is that? So let's consider the forces acting. Let's say that our normal force is N. I'm just going to label that. So I'm going to say the normal force N is greatest. And if we just apply Newton's second law, which state that the net resultant force will be essentially the sum of all the forces. So if we have mg going downwards, we'll also have n acting upwards, and those two forces will need to take them away from one another. So using Newton's second law, we can say that n, the normal force, take away the weight, mg will be equal to mv squared divided by r, which is the radius, which means that n will be mv squared over r plus mg. Now, similarly, the normal force will be the least at point A. So at A, n will be the least. And we can use exactly the same logic. So at point A, both the normal force and the weight are acting in the same direction, because if we have mg acting downwards, I do realize I'm drawing these vectors at a little bit of an angle, so let's just make this precise. If n is acting this way, then mg will also be acting the same way, so we'll need to add them up. So we can say that the net resultant force will be equal to n plus mg will be equal to mv squared over r, meaning that n will be mv squared over r, take away mg. Okay, on to the next question. Okay, on to question 2, which is actually question 2 from a paper from 2010. Okay, so figure 2.1 shows an airplane flying in a horizontal circle at constant speed. The weight of the airplane is W and L is the lift force acting on at right angles to the wing. Explain how the lift force L maintains the airplane flying in a horizontal circle. The word horizontal has been written in bold. Now, if that's the case, well, we can say that L will be represented by two components. So this is actually essentially a vectors question. This component, the vertical component of L, will have to be equal to the weight of the airplane. So the two will cancel out, and the horizontal component will be providing the centripetal force. So this here will be Ly, which will be equal to the weight, and Lx will be providing the centripetal force, mv squared over r. So let's just write this down. So we can say that the vertical component of L is balancing the weight, and the horizontal component is providing the centripetal force. So, in other words, this Lx component, the horizontal component, is making the airplane turn, and Ly is keeping it at the same height, and therefore the airplane is turning in a horizontal circle. The airplane has a certain mass, 1.2 times 10 to the 5 kg, flying in a horizontal circle of radius 2 kilometers. The centripetal force acting on the airplane is 1.8 times 10 to the power 6. Calculate the speed of the airplane. So what I'm going to do is use F is equal to mv squared over r, meaning that v squared will be equal to fr over m, meaning that v will be equal to the square root of fr over m. And let's plug in some numbers. So f is 1.8 times 10 to the power 6. The radius is 2 kilometers. Let's not forget to convert that. So it's going to be 2.0 times 10 to the power 3, and let's divide that by the mass, which is 1.2 times 10 to the power 5. and this is going to give us 173 meters per second. In this case, we're working up to two significant figures, so let's leave that as 170 meters per second. Now, part B of this question I actually solved in my previous video from yesterday, and this is because it delves into gravitation, so it's part of my question pack or my video on solutions on the gravitational topic of gravitation. So have a look at that if you're looking for part B of the solution. Okay, on to the next centripetal forces question. Okay, on to the next one from June 2011. Once again, you can find this question in the description of this video. Okay, so part 1a, state Newton's first law of motion. Remember, a body will remain in a state of rest or continue to move at a constant velocity unless there's an external force that is acting. Define the Newton, the force required to accelerate a mass of 1 kg to an acceleration of 1 meters per second squared. Anytime I'm asked to define a unit, such as the Newton, just over here on the side I will write down. All I do is just write down an equation, for instance, F is equal to ma, I rearrange for, well, this is already rearranged for the force. We can see that 1 Newton is defined as whenever 1 kg is accelerated to 1 meters per second squared. Okay, part B, we have a jet plane on the deck of an aircraft carrier is accelerated before takeoff using a catapult. Exciting, the mass of the plane is 3.2 times 10 to the 4 kg. It's accelerated from rest to a velocity of 55 meters per second in 2.2 seconds. Calculate the mean acceleration of the plane. Now, assuming that the acceleration is constant, we can just use the Suvat equations. For instance, we could just use v is equal to u plus at, and given the time, so it's accelerated from rest, so we know that u is equal to 0, and we can just essentially just rearrange for a. So a will be v minus u divided by t. This is the definition of acceleration, really, and our speed, our final speed is 55. Take away, well, 0 divided by t, which is 2.2. Plugging that into a calculator, well, we're going to just get about 25 meters per second squared. Okay, next one, the distance over which the acceleration is actually taking place. So let's use the Suvat equation for distance. So s is equal to ut plus a half at squared. And in this case, u is just equal to 0, so we can essentially forget about this term. And what we're going to get is that this will be equal to a half times the acceleration, which is 25, multiplied by the time, which is 2.2. We're going to square that, and if we put this into a calculator, we're going to get about 60.5 meters, which is our answer. Next one, the mean force producing the acceleration. Well, this one is easy peasy. So F is equal to ma. We're given the mass of the airplane to be 3.2 times 10 to the power of 4. So 3.2 times 10 to the power of 4 multiplied by the acceleration, which is 25. That's going to be about 8.0 multiplied by 10 to the power of 5 newtons. Okay, the jet plane now describes a horizontal circle. So this was just almost a little bit of a revision to the Suvat equations, which is always very, very useful. Now let's get on with the actual circular motion part of the question. The jet plane describes a horizontal circle of radius 870 meters flying at a constant speed of 120 meters per second. State the direction of the resultant force acting on the plane, and this is always towards the center of the circle. Like so. Calculate the magnitude of the horizontal force, which is going to be using F is equal to mv squared divided by r, and we're given the mass of the plane. It was 3.2 times 10 to the power 4, so it's going to be 3.2 times 10 to the power 4 multiplied by 120 squared. Let's divide that by 870, and plugging that into a calculator up to 2 sig figs, we're going to get about, just write it in the answer box, about 5.3 multiplied by 10 to the power 5 newtons. Okay, so part D, by changing the velocity of the plane, it can be made to fly in a vertical circle of radius 1,500 meters. So now the pilot is essentially doing a loop and state and explain what point in the circle the weightlessness may occur. So imagine that the pilot is doing a vertical circle. How exciting. The weightlessness would actually occur at the top of the circle. So we can just write this down. So it will occur at the top of the circle, and the reason for that is because at that point the centripetal force F is fully provided by the weight. So for a brief moment the weight is making the airplane turn, so we can just say that the centripetal force is provided by the weight and equal to the weight. Perfect. Calculate the speed of the plane at which weightlessness occurs. Well, in order for apparent weightlessness to occur, everything around you needs to be falling at g. This is why the astronauts at the space station do not feel gravity. They're still in a gravitational field, however everything around them is falling at the same rate. So the centripetal acceleration will be equal to g, which is 9.81. Now the centripetal acceleration is just v squared over r, not mv squared over r, so let's just write that again. So v squared over r is going to equal to 9.81, and we can just rearrange for v. So v will be the square root of so 9.81 times the radius, which is 1,500. That's going to give us about 120 meters per second. Okay, on to the next question. Okay, next one, which is question 3 from, I believe, 2012. So we have this apparatus in which we have a glass tube and we are spinning a bung with a mass connected to the bung by a string. Part A, draw an arrow labeled F on the figure to indicate the direction of the resultant force on the bung. Now the direction of the resultant force will be always towards the center, and we're not going to forget to label this. Number 2, explain how the speed of the bung remains constant even though there is a resultant force F acting on it. This is actually a really typical question, so it's important to make a note on how to answer this. Now, when the bung is actually moving, the force is always at 90 degrees to the speed. So you can imagine the speed kind of going into the board. Obviously can't draw it in 3 dimensions, but at any point the velocity v is perpendicular to the speed f. So how are we going to answer this? We can just say that the resultant force, so let's call it the net force, F is perpendicular to the velocity, so there won't be any work done. It's perpendicular to the velocity and no work is done by the force. Okay, part B, 2 students carry out an experiment using the apparatus to investigate the relationship between the force F and its speed V for a constant radius. They describe how they obtain the values of F and V. Now, the way to go about this experiment is, first of all, to keep the radius constant. One way of doing that is by keeping a reference mark at exactly the same position within the tube. So I'm just going to mention that. So keep the radius constant. So we can say that, keep the radius constant by keeping the reference mark in the same position. Mark in the same position. So after we've kept the radius constant, we can actually calculate the force that's acting, the centripetal force, essentially, because if this thing is in balance, then the centripetal force will be equal to the weight. So we can just calculate this using mg, where m is the mass of the attached, essentially, masses. Okay, then in order to measure the speed, we're going to need to measure the time period. However, this normally is very difficult to measure, so I'm going to say that we will measure 10 time periods and divide by 10 to reduce our percentage uncertainty. So to reduce the percentage uncertainty. Finally, we're going to calculate the speed v using v is 2 pi r over the time period. One final thing I've not fully mentioned is that we need to measure the radius r as well. So I'm just going to add an extra point here. That will be to measure the radius r with a ruler. Okay, and now we're done to take measurements of both f and v. Part 2, sketch on figure 3.2 the expected graph of f against v squared. Well, this should be a straight line through the origin because f is equal to mv squared over r, and if y is equal to mx plus c, we can see that the gradient, let's give the gradient a different letter, because m is already in use for the mass. I'm just going to call it grad. Our gradient will be m over r because f is on the y-axis, v squared is on the x-axis, and the intercept is 0. Explain how the graph can be used to determine the mass of the bunk. So we'll just say calculate the gradient. And then our gradient is equal to m over r. Therefore, the mass of the bung, m, is equal to our gradient times r. Okay, next question. Okay, our final question for today is actually from a paper from 2014. This is question 2. Now, the first part of this question is mainly using Newton's laws and SUVAT, and because this is a video mostly focused on circular motion, I'm going to start with part C. We're going to need the fact, though, that the mass of the airplane is 6,200 kg, which is given in the previous part of the question. So I'm going to write this down over here, that the mass is equal to 6,200 kg. Okay, so we have the jet is used in a flying display in which the pilot will be required to fly the jet in a horizontal circle of radius r, and we have the constant speed of 86 meters per second. This is achieved by flying the jet with its wings at 35 degrees to the horizontal, and then we're looking to show in the first part that the magnitude of the force L is approximately 74 kilonewtons. Okay, well, let's analyze this motion. So this lift force L will once again have a vertical component and a horizontal component. The horizontal component will be making the airplane turn. This will be providing the centripetal force, and the vertical component will be balancing out the weight. Now, a slightly better way to actually draw the vectors would be along here. So this here will be the vertical component of L, and this here will be the horizontal component of L. I'm going to say that this here is L cos of 35, and this here is L sine of 35 because it's the opposite component. So in order to show that L is 74 kilonewtons, what we can use is that because the airplane is flying in a horizontal circle, L cos 35 will have to equal to the weight. So we can just say that L cos 35 is equal to mg. Therefore, L is equal to mg over cos of 35. The mass was 6,200 times 9.81 divided by cosine of 35, and that's going to give us about, well, 7.4 times 10 to the power of 3, so 10 to the power of 4, sorry, so which is approximately equal to 74 kilonewtons. Okay, right, next one, calculate the radius r. Now, chances are we'll need to use the other component, which is L sine of 35, and this will be providing the centripetal force. Well, are we given the speed? Yeah, we're given the speed, so what we can just write is that L sine of 35 is equal to mv squared divided by r, and we already have L, so we can just rearrange to find the radius. So our radius will be equal to mv squared divided by L sine of 35. Now the mass is 6,200. Multiply that by v, and let's see, the speed is 86 squared. Divide that by 74 times 10 to the power of 3 multiplied by sine of 35. We're going to find a radius of about 1.1 kilometers or 1,100 meters. Okay, on to the next one. So very similar to one of the previous questions that we solved earlier in this video. A more complex maneuver, loop. The pilot is required to fly in a vertical circle at a constant speed as shown in the figure. For a certain speed, the pilot can experience a sensation of weightlessness at a particular point along the circle. On figure 2.3, mark with a cross labeled A, the point where the pilot experiences the sensation of weightlessness. Now this occurs at the top of the circle, and state the magnitude of the vertical component of the contact force exerted by the seat on the pilot at A. Well, this is going to be 0 newtons, because at this point all of the turning effect is fully provided by the centripetal force, so there's no contact normal force. Okay, part 2. In this maneuver, it is convenient to analyze the motion of the jet in terms of the two forces: a constant weight W, a variable force P, which is the resultant of the engine thrust, the lift from the wings, and air resistance. At the point B in figure 2.3, the jet is flying vertically upwards. Explain why the force P is not directed towards the center of the circular path. Well, the only force that will ever be directed towards the center of the circle will be the resultant centripetal force, and P is not that force. And we can see that because P is the resultant of the engine thrust, the lift, and air resistance, but does not take into account the weight. So we can just simply say that P is not the resultant centripetal force. Like so. Okay, folks, well, we've actually solved a lot of the circular motion questions from the old spec of OCR Physics A. Have a browse through the newer papers on their website and through some other exam boards to get some extra practice. But well done for following this video. Thank you very much. I hope these videos are useful. If they are useful, give them a like and please consider subscribing. Thank you very much, and I'll see you in the next video.